Hi, thank you so much for attending my presentation. My name is Antunez-Garcia, and the title of my presentation is The Effect of Chemical Composition on the Properties of LTA zeolite, a Theoretical Study. Zeolites have a wide range of practical application, for example, in sewage treatment, fertilizers, animal husbandry, paint, pharmaceutical development, automotive parts, detergent, catalyst in the petrochemical industry, sensor, aesthetic product, nuclear waste storage, and novel solutions against viruses and bacteria. Zeolites are microporous crystalline solids with well-defined structures. Most zeolites have pore size from 1 to 10 angstrom. Generally, the zeolite framework is composed of silicon, aluminum, and oxygen. However, other trivalent elements such as iron, boron, or germanium can also be included in their matrix. The most basic structural unit in zeolites is the tetrahedron, which, together with other tetrahedrons, can give rise to more than 200 different zeolites currently known. On the other hand, aluminum is an element typically observed in the framework of natural zeolites. However, its trivalent nature requires an extra framework cation to compensate for the charge deficiency. The most common is sodium. The problem of atomic species distribution in zeolites. While the crystallinity and pore size is decisive for choosing a certain zeolite for a particular purpose, determining the distribution of atomic species in the framework can clarify phenomena such as ionic transport or catalytic process. It can also help to understand the constraints in the synthesis to give rise to a specific crystalline structure effectively. The latter can lead to the development of inexpensive and low-cost synthesis methods. In principle, there is more than one way to distribute aluminum in a zeolite framework. According to them same studies, in terms of Madelung energy, aluminum atoms cannot be randomly distributed in the zeolite framework, but they must also satisfy the Lowenstein's rule. This rule implies that two aluminum tetrahedrons cannot be immediate neighbors. The most commonly synthesized LTA zeolite is called sodic LTA or sodic A and has a silicon-aluminum ratio equal to 1. Particularly in this work, we are interested in evaluating the Lowensteinian and non-Lowensteinian configuration for the sodic A zeolite. According to ISA database, this is the unique cell representation for the LTA zeolite. The problem is that from this, it is not possible to construct a Lowensteinian configuration for the sodic A zeolite. If one wishes to do so, one would have to construct a supercell by expanding this cell 2 times in all 3 directions. Here is just sketched just in 2 directions the expansion of this unit cell. For optimization purposes, we will be dealing with a considerable number of atoms. In the present work, we propose an alternative rhombohedral representation cell for the LTA zeolite. This is our representation, in which both configurations can be evaluated with more acceptable computational cost. Purpose of the present study. First, investigate the validity of the Lowenstein rule in sodic A zeolite. Second, to investigate the effect on the electronic properties of introducing 1 and 2 iron atoms in sodic A zeolite matrix. By introduce, we mean the isomorphic substitution of silicon by iron cation. Theoretical considerations. The calculations were carried out using the quantum space code. The electronic state were expanded in terms of plane wave with an optimized kinetic energy cutoff of 45 Weber and considering a charge density cutoff of 360 variable, PV Sol exchange correlation potential was used. All atoms were relaxed until the residual force were below 1 to -3 Weber by angstrom. The convergence tolerance in the calculation was set as 1 to -6 Weber per atom. More detailed information can be found on this reference of our already published work. Results. This figure sketches part of the non-optimized structures for the Lowestinian and non-Lowestinian configuration for sodic 8 zeolite. As can be seen, for the Lowestinian, the silicon and aluminum atoms are uniformly distributed, while for non-Lowestinian configuration has aluminum tetrahedra neighboring each other. On this side, the respective optimized configuration, including the sodium cations, can be seen. If both configurations are contrasted, some structural change can be observed. For example, in this part, compared with this part, or the size of the bonds is slightly different, larger. Additionally, it's observed that on average, the sodium-oxygen bond distance are relatively smaller in the case of the non-Lowestinian configuration. So interestingly, our results show that the non-Lowestinian configuration is energetically more favorable. As previous work, similar previous work, shows that also that the non-Lowestinian configuration is energetically more favorable. This figure compares the experimentally obtained diffraction pattern for the solid A zeolite versus the simulated diffraction pattern for the Lowestinian and non-Lowestinian configuration. The figure showed that much of the pattern of the experimental sample is reproduced by optimized theoretical models. On the other hand, the contrast of the theoretical diffraction patterns exhibits certain differences that could be used to further interpret the experimental results. In this figure, we compare the total density of state for all the configurations under study. This is the case for pure silica LTA zeolite. This is the case for a sodic A zeolite with Lowestinian and non-Lowestinian configuration. When one silicon and two silicon cation are isomorphically substituted by iron cations. Roughly speaking, it is observed that when aluminum is introduced in combination with pure silica configuration, the band gap is considerably reduced. However, when iron is introduced, not only the band gap is reduced to zero, but also magnetic properties are exhibited. In this figure, a magnification around the Fermi level has been made to obtain more detailed magnetic behavior. Both figures show the separation spin channels, alpha and beta, or up and down, in a non-symmetrical way. In particular, for the fifth case, only the spin down grows the Fermi level. So this particular behavior is known as a half metal. For the second case, when two iron is introduced in solid A zeolite, both spin alpha and spin beta contribute in different proportion. So at least we have a dominant polarization. This table shows the different band gap values for the different configuration under study. In particular, it observed that the band gap for the non-Lowestinian configuration is lower than the Lowestinian configuration. Figure 7a shows the partial density of state evaluated specifically at the Fermi level for the different type of oxygen, O1, O2, or O3, as a function of configuration type. Pure silica, low Einsteinian configuration, no low Einsteinian configuration, when one iron atom is present in the zeolite and two iron atoms is present in the zeolite. The figure shows that for pure silica case, the oxygen have the higher participation of the Fermi level and decrease with the introduction of aluminum and iron atoms. Specifically, when iron is introduced, the participation of oxygen is practically zero. Figure 7b shows the partial density state contribution of the remaining atomic species at the Fermi level as a function also of the different configuration. The result shows that compared to oxygen atom, silicon, aluminum, and sodium atom contribute very little. However, when iron is introduced, as we said, in this case, the oxygen atom contribution goes to zero. Iron takes the control of the electronic conduction in the zeolite. Figure 8 shows the loading chart for the different atomic species. In this case, I have the oxygen, again, oxygen only in figure A, and the remaining species in figure B. Loading charts tell us that the higher its value, the more occupied the valence shell is, and greater the probability it has of donating an electron. This means a basic character. Conversely, the lower value, the higher the probability of accepting an electron is. This figure shows that when aluminum is introduced into the zeolite, the oxygen exhibits very basic behavior. This presents the higher value for loading charge. In both cases, low Einsteinian and non low Einsteinian case. When iron is introduced, the loading charge in oxygen atom decreases. For pure silica LTA zeolite, not only his behavior is very acidic, but also inverse the trace. The trace is inverted. So this is a very interesting behavior that we found, which maybe is associated with the hydrophobic nature of the pure silica case. For the other species, they gain acidity when aluminum is introduced and also when iron is introduced. This help to explain that when aluminum atom and iron atom is introduced, the band gap is also reducing. Conclusions. The results show that the non-low Einsteinian configuration is energetically more favorable and exhibits a smaller conduction band gap as compared to the low Einsteinian configuration. When silicon cations are isomorphically substituted by iron, the zeolite displays a magnetic behavior. However, the two different frameworks on the consideration exhibit distinct magnetic nature. It was also observed that the zeolite framework containing iron-3 cations present a higher acidity than aluminum one. Thank you so much. I'm at your disposal for any questions you may have.